Good morning, mathematicians. I realized I lied a bit on Wednesday because I was promising things. I was like, "Oh, tomorrow stream, tomorrow stream," but I don't stream on Thursdays because I'm busy. So I'm here to make good on at least one of my promises. The question about the ring of compact functions was resolved IRL. Maybe I'll still talk about it at some point. It's a good exercise, but I do want to make good on my promise about doing a computation with perverse sheaves. So that's what we're gonna do. Yeah. As soon as I get things adjusted, yeah. But I'm gonna try and I'm probably gonna try and keep the stream short because I got things I want to do today. Actually, I have things I want to do every day. But I wonder if I should wait a minute for people to jump in. I mean, the person who asked the question, I don't even know if they'll be here. But the recording will be available, so let's dive into it. So here's our situation. The variety that we're dealing with is going to be just 2x2 complex matrices, and we're going to take a stratification. So we're going to write X as a disjoint union of three locally closed varieties, where C0 is just going to be all of those matrices of rank 0. So in particular, it's just the singleton 0 matrix. C1 is just the matrices of rank 1. So in other words, it is those matrices whose determinant is 0, but A is not the 0 matrix itself. And then finally, these will be the invertible matrices. That is, those matrices of rank 2, i.e. those matrices whose determinant is not equal to 0. And what we're going to do is, in each case, we're going to try and understand the perverse sheaf given by the intersection cohomology complex on each of the given orbits with respect to just the trivial local system, right? So the recipe is you always start with sorry, I'm calling them orbits because actually this example comes from some group action, and secretly I care about equivariant objects with respect to the group action, but so I apologize if sometimes I slip and I call these orbits. These are actually orbits under some group action, but that's not. I'm trying to throw away as much of the fluff as possible that I care about. Well, it's not fluff, but like, yeah, I'm trying to just get straight to the point with the actual computation. Okay, so how are we going to do this? Well, last time I mentioned a couple rules, a couple easy tools for computation. So one of the general rules I think I mentioned last time is if the closure of C is smooth, and if you have a local system that lives on the closure, which is irreducible, then the restriction back down to C should still be irreducible. And, well, actually, you don't need it to be irreducible to do the computation. It's just, so that's another little sprinkle of the conditions that I care about, but that's not actually necessary. You could just take any old local system. I mean, this is true, and I care about it, but if you take any old local system on the closure, restrict it, and then take that IC, and if J is just the inclusion into X, then this will just be the underived proper push forward of that local system shifted in the dimension of your orbit. So that makes two of our computations up above really easy. So in particular, C naught is equal to its own closure, and so the trivial sheaf, of course, the trivial sheaf, which is just like the skyscraper sheaf at the point, or you could say the constant sheaf on the point. This is a local system on the closure, and of course, when you restrict it, well, nothing happens. You just have the exact same thing. So this theorem immediately applies, and we can see that the perverse sheaf of the constant sheaf on the strata being just a single point, that is just going to be, well, it's the, I mean, I'll just sort of maybe abusively still write it as 1 sub naught to indicate that this is the skyscraper sheaf. Well, really, I mean, this is supposed to be a complex, right? So this is a complex concentrated entirely in degree 0, and the thing that you put in degree 0 is just the skyscraper sheaf. So that's an easy computation. Likewise, the if we consider, there's an important thing I also didn't tell you, is that I is less than J if and only if Ci is a subset of Cj closure. So in other words, right, we saw C1 is closed, or sorry, C naught is equal to its own closure. The closure of C1 is C naught union C1, but we're going to skip that for a second, do the easier orbits first. And then C2 closure is C1 union C naught. I did this in a in a stupid order, but oh well. Which is the entire variety that we started with. I hope I said it out loud, but this is everything I said here. Sorry, everything I said here requires C bar to be smooth. Everything I said right here requires C bar to be smooth. That's very, 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 very important. Yes, it's super false. It's super false if C bar is not smooth. Yeah. So right. So the point was C bar. Certainly, just a single point is smooth, right? So we were able to apply that in this case. Here, this is the collection of matrices of rank at most 1, and this has a singularity at the origin. So oftentimes when we're doing these sorts of stratifications, we I don't even want to say it's definitely not always the case, but yeah. Okay, whatever. The point is, it has a singularity. It has a singularity picked up from the other orbit. But then the closure of C2 is just the entire space, and so that's smooth. And so we can go ahead and apply our theorem. So we take the IC. Oh, I wonder if I should plug in to enhance stream quality. Wow, Chad is dead today, gang. Chad is dead. It's not even the weekend. Okay. So, oh, it is alive. Okay. Well, thank you for keeping Chad alive, Deepak. So I see of the trivial sheaf on the strata C2. Again, we can apply this same trick, but now, also I made another mistake. The J up here should be from C bar. That's the other mistake I made. Right. So a mic, a haircut. I did not get a haircut. My hair is just wild. I've always had this mic. Maybe it's just not always as in view as it should be. I feel like the audio quality is better when I'm nice and close. So, I'm not a true podcaster yet. One day. It'd be great to have famous mathematicians. Like, there's this one. I'll fill you in 1 sec. But there's this one great conversation. I want to do something like this at a conference one day. I could have at the last conference I went to. There was some like, there was some, there was a bunch of big names. Oh yeah. So there's this is like a conversation that was recorded in the 90s. Yeah, I guess Abdus Salam won the Nobel Prize that year. But so these four big names in physics, you just sat down in a room and someone just turned on a camera and they just had a free-flowing conversation, and it was awesome. Actually, there's another good one. It's a little more formal than that one. Like I would want to do one like the one I just mentioned. Yeah, but there's this conversation. You can see there's David Vogan there. I think that's Harish Chandra's daughter. Yeah, a bunch of other absolute giants. Absolute giants of mathematics. And they're just having a free-flowing conversation, and it's awesome. What have I been working on in my Ph.D.? Well, I'm the point of streaming today is to highlight an example. I mean, this is one little piece of it. In short, it's about the local Langlands correspondence, and some geometric manifestations of it. But right now we're going to zoom into a tiny little piece of that, and we're doing a computation with perverse sheaves. So I apologize for those viewers who this is way beyond where you might be at, but just to get you somewhat caught up, we're looking at 2x2 matrices. We've stratified it into 3 strata, being the rank 0 matrices, the rank 1 matrices, and the rank 2 matrices. It definitely involves a lot of algebraic geometry, but it's algebraic geometry that's motivated by the representation theory of p-adic groups in a strange way. Yeah, you basically the thing I sort of care about ultimately is representations of p-adic groups. But then, assuming the local Langlands correspondence, you transform this into statements about algebraic geometry. And And I was just using a little trick here about, you know, whatever the hell a perverse sheaf is supposed to be. It's some complex of sheaves. And I have a very special trick when the strata we're looking at, when it's closed. We have a nice little trick with the computing the perverse sheaf of a local system. It allowed us, for example, to simply conclude that for the rank 0 orbit and the trivial sheaf on there, whatever the intersection cohomology complex is supposed to be, actually it's going to just be, it's a complex concentrated entirely in degree 0, and the sheaf that you put into degree 0 will just be the skyscraper sheaf at 0. Likewise, so just to explain this theorem, if you have a local system on the closure, and we don't really need irreducible, but that's a word I care about, then if you restrict it back down to C, take the intersection cohomology complex of it, it'll just be that local system concentrated in the degree of the dimension of C, but then you just push it forward from the closure. Push it forward from the closure into everything. So this should be, right? Well, in this case, again, because I'm just computing for the trivial sheaf, certainly we can consider just the trivial sheaf on all of X, right? Like, by which I mean the constant sheaf. I should say trivial local system, because trivial sheaf might mean the 0 sheaf, but the constant local system, trivial local system. And of course, if we restrict that back down, we get the constant local system on C2. Maybe I should have been notating that. But then the push forward, right, from the closure. Well, the closure is all of X, so this is just the identity. So all of that to say is that we can use the above theorem to conclude that this is simply going to be the constant sheaf on all of X, but we need to shift it in the dimension of our orbit, of our strata of C2, and I guess C2 has dimension 4 because it's an open subset of the 4x4 matrices. I have not read the Dedekind-Weber 1882 paper. What's the Dedekind-Weber 1882 paper? Maybe I should know that. I'm gonna try to not get too distracted. I mean, let me know in the comments. But I'm also trying to get this one computation done just because I promised it, and then run off. I want to try and I have 2 back-to-back mentorship meetings for some undergrads that I'm mentoring, and then before that I have a chess game for a departmental chess competition, and before that I want to try and hit leg day. So it's gonna be an intense couple of hours. Okay, so the trick that doesn't work is now, as I mentioned, the closure of C1 is this has a singularity at the origin. It has a singularity at the point being the 0 matrix. So what are we going to do about that? We're going to use our friend, the decomposition theorem. Sure, yeah. I mean, please bring it up. Please bring it up another day. Well, I see, people who are interested can find it based off of that. Yeah. Yeah, I don't know if I've ever read math that old. Reading math that old is hard sometimes. Actually, it's surprisingly clear on occasion. It's not like the 1400s where all math was written in poetry or whatever. Okay, so the decomposition theorem basically tells us that if we take a resolution of this orbit, a smooth resolution, and we want this map to be proper as well, then if we take the push forward, is ordinary push forward, shriek push forward, it might not matter, of the constant sheaf, shifted by the dimension of this thing, then this will be, I'll be maybe even a little more precise, this will be a direct sum of simple perverse sheaves, which is to say intersection cohomology complexes, and, well, I guess technically I thought I was being clever and circumventing absolutely everything to do with the equivariant perverse sheaves that I actually care about. But now I'm worried that here in the decomposition theorem, technically I want to make use of the equivariant decomposition theorem, which cuts down our search space. So let me explain. Okay, let me say it this way. So we know that it will be a direct sum over two things. So first, it'll be a direct sum over each of the simple perverse sheaves. But then also, we have to consider each possible shift of that perverse sheaf, and that shift will be to some multiplicity. So maybe we could even imagine that we have some, I don't want to say they're necessarily countably enumerated, though they probably are. Actually, I don't even think that's true, but let's call this pi, and let's call this mj for the jth shift of the ith perverse sheaf, and then this will be to some multiplicity mij. So maybe I shouldn't call this one m as well, but okay, too late. Yeah, I think you get the idea, right? The decomposition theorem, the bare bones decomposition theorem, tells us that we'll get pushing forward this thing will just be some sum of shifted perverse sheaves with multiplicity. And hopefully this will allow us to determine what our missing intersection cohomology complex looks like. Now, the problem is actually in the full theory, I guess there's potentially a lot more sheaves than I'm used to working with, because for each one of these orbits, take a point in the orbit. It turns out that the category of representations of the fundamental group is equivalent to the category of local systems on the orbit. And so this is one way that you can determine said local systems. And, well, that's not really a big deal for the closed orbit because the fundamental group is trivial. It's also not a big deal Well, now I don't even know what's the fundamental group of GL2, GL2C. It's Z. Interesting. Okay, so that's got a lot of representations. Right. So that would be problematic because I would have to like consider the local systems corresponding to all of those representations. Where'd chat go? I'm trying to, so that would make life difficult for me. But actually, maybe not. Maybe it's easier than that. Okay. Well, I guess I need to do some homework. But I'm now going to cheat by imposing the fact that so secretly. Let me move over. Here's the cheat bar over here. Damn, I really need a new color. I feel like there should be a more orangey orange. You know what I mean? Why don't they give me a more orangey orange? I'll try this one. Okay, secretly X is being acted on by 2 copies of GL2C. Why? This just comes out of my research interests, where AB is acting on X by AXB inverse, and it's still the orbits still give you this stratification, but now the thing is, I only care about what are called equivariant perverse sheaves, which I'm not going to talk about today for the sake of time. And I also care about equivariant. So, and it turns out, well, how do you build those equivariant perverse sheaves? Well, the simple ones will just be the push forwards of some local system on the orbit where L is an equivariant local system. And it turns out, in this case, whatever the hell that happens to mean, the only equivariant local systems on the respective orbits, so let me write this, C0, C1, C2, are just the constant sheaves. And then the equivariant decomposition theorem tells me that I only have to worry about the equivariant perverse sheaves here. So I'm going to use this little trick or cheat, and I guess I'll have to do my homework because I don't. It's actually funny. I don't think I've ever done. I don't think maybe never done computations with non-equivariant perverse sheaves, which is kind of funny because it's like, well, you think you'd learn normal perverse sheaves first because those are probably less complicated. Yeah. But actually, yeah, I mean, there's probably a way to make all of this work just the same. But the point is this. We're going to have a bunch of shifts. So it'll be the ICs. We'll be ranging over the ICs of CI. We'll just be taking the constant sheaf on that orbit. a priori will be allowing some shift in the degree. So maybe I should call this dj. And then putting that to some multiplicity mij. And I claim that this is going to help us figure out what the IC of the corresponding to the rank 1 matrices is. So how is that going to help us? Well, so first off, we should choose a cover, but in fact, we should choose a very important cover. That is, we want to choose it so that it's semi-small. What does semi-small mean? That means that for every orbit in the closure of C1, so really that just means for C0 and C1, we have the formula. Let's see if I can do this from memory. It's the dimension of C tilde. I think here will be the dimension of D, and this will be 2 times the dimension of the fiber of a point where X is in D. I'm pretty sure this is our formula for semi-small, if I'm remembering correctly. And the nice thing about that is the semi-smallness says that the only shifts that appear are zeros. So that will make our life a lot easier. Actually, I think in this example you don't even need semi-smallness. I think you can just do this computation and get away with things as they are because it's like small enough. The sheaves are manageable. But whatever, this is a technique that definitely makes our life easier in general. So may as well mention it. So what is the cover that we're going to take? So C tilde of 1 is going to be the space of all matrices A together with all vectors V, where so this will be in C1 closure, so matrices of rank at most 1, and this will be in P1, complex projective, or maybe the 1 should go up here. Space, subject to the condition that A times V is the 0 vector. So what I mean by that is I'm coordinatizing projective space to be vectors of this form, where of course, you know, this is equal to some non-zero scalar multiple, and not both coordinates are 0. And then the map will just be projection on the first factor. So, okay, this is very not rigorous, but this is, you know, we're basically just multiplying by a copy of projective space. So it's going to be a proper map. Actually, I think in the complex analytic case, it is basically as easy as like saying your fibers are projective or something. It's easier than in algebraic geometry, I think. Great. So that's going to be our map. Let's see that it's semi-small. Well, first let's check C1. So we want to take an arbitrary point of C1 and look at the dimension of its fiber. Well, the fiber is over an element of C1 is just going to be all. It's basically just going to be the collection of all of those V, all of those points in projective space, such that this is equal to the 0 matrix. Maybe I should write it on that end. But if we multiply that through, this is just B0. But this is projective space, so that's the same as this point. So the fiber has dimension 0. And, well, the dimension the dimension of this space, I mean, it's at least as big as C1 bar. But we're possibly, like, if we didn't have this condition, we'd just be multiplying it by something of dimension 1. So in fact, this has the same dimension as C1, being 3. Yeah. So in this equation here, well, this term is 0, this term is 3, and this term is 3. Great. So the map is semi-small. Meanwhile, if we look at the closed orbit, well, that dimension, the dimension, we're looking over C0 now. Well, that thing's dimension 0, right? Plus 2 times, well, what's the fiber? The fiber is going to be, well, of course, this is just the zero matrix. So every point in projective space satisfies this. So this will just be a copy of projective space. So this will just be 2, right? That's one dimensional times 2. And that's less than 3. So great. So our map is indeed semi-small. We've checked it for all the orbits. What am I trying to say here? Oh, yeah. And then the other thing is, in fact, because we don't have a strict equality here, we say that this orbit is irrelevant. So it's been like a year and a half since I did this, so I don't remember what that... Somehow we can drop it from our computation, and actually life becomes even easier. Again, I don't think we even need to. Like, I don't even think we need to use semi-smallness at all in this example, but again, it's a useful tool in general. Okay. So, let's put these things together now. So, we have our push forward. And we know, well, we have to shift this in the dimension. It's 3-dimensional. And we know that this map is semi-small, so there's not going to be any shifts. So there's just going to be IC. So let me, as a shorthand, let me write ICI to mean IC of CI constant sheaf on constant sheaf on CI. So what am I saying? Yeah, so this will be IC1 with some multiplicity. Let me just call it M1, or sorry, IC0 with some multiplicity, summed with IC1 with some multiplicity with IC2 with some multiplicity. And actually, I'm just realizing now I might have said some lies earlier, as I often do. I said this was 4-dimensional. Yeah, that's right. Yeah, that's right. Sorry, that wasn't a lie. That's 4-dimensional. Okay. Okie dokie. So now what I'm going to do is I'm going to take stocks of both sides of this equation. So let me take a stock at C1. So I'm gonna take the stock at some point of C1. The left-hand side, this is just like a fact about pushing forward the constant sheaf, that this will be the cohomology sheaf. When we restrict this to the orbit, it'll just be the cohomology sheaf of the inverse image of pi. That's like a general fact. And so in particular, once we go down to a stock and we just view everything as a graded vector space, this will just be the cohomology of the fiber of X. But I mean, we already saw that the fiber of X over a point in C1 is just a point. So as a graded vector space, this will just be a copy of the complex numbers concentrated in degree 0. IC0 restricted to X, well, we saw that that'll just be, that is just going to be, well, maybe I should do this in terms of graded vector spaces, right? This was just the constant sheaf on, this is like the skyscraper sheaf on 0, shifted in degree 0. So we'll just get a copy of C0, C0, M0, direct summed with, okay, this is the stock that we're trying to figure out. So IC1 restricted to some point, and some multiplicity, which we don't know yet. M1. And then IC2, remember IC2 was just the constant sheaf on the whole thing, shifted in dimension 4. And so that means that when we take this stock, we'll just get a copy of this vector space in dimension 4. But this equation has to hold, right? As graded vector spaces, there's no degree 4 piece over here. So we can conclude from this that M2 is equal to 0. And we have two possibilities. Either, so there's two choices. It could be that because we see a degree 0 piece here, right? So M0, it's at most 1, right? It couldn't possibly be 2 because then we have we'd have too many copies of a vector space in degree 0. So it's at most 1. If it were equal to 1, then M1 would have to be 0. There'd be no room left for this one. So that's possibility number 1. The other possibility is, in fact, that M0 is equal to 0. But then that M1 would be equal to 1, and we would know that the stock of this IC at X would be in degree would be this. And actually, yeah. So here's where the smallness comes into play. Actually, so I believe the fact that we found that for C0 that we had that this was strictly smaller, I believe that tells us immediately. Yeah, that's where that comes important. I believe that fact tells us immediately that this is equal to 0. And therefore we can conclude that this is true. So yay! So that has helped us. We don't know, like, this is some mysterious complex of sheaves, but now we know whatever that complex of sheaves is. We can it has like a copy. It's in its degree 0 component. It has a copy of the constant of the constant local system on C1 in degree 0. Yeah. And so finally, okay, I want to this hasn't been the same kind of office hour as usually with, back and forth and open questions, and I apologize for that, but like I said, I wanted to make good on my promise to matrix coefficient that I would explain some of these things. And so finally, we just, I'll just quickly say that we just repeat this process. Oh, wait a second. Did I make a mistake about the shift? Wait, this is in degree 3. Oh, sorry. Crap. This was supposed to be in degree 3. What am I doing? This was supposed to be in degree 3. So this was supposed to be in degree 3. So, okay, this part of the argument still works. M2 is equal to 0. But, oh, and then, I mean, we know, actually, so we didn't even need to use the smallness. We're immediately forced into concluding that M0 is 0. And in fact, sorry, this should be in degree 3. And so, sorry, this should be in degree 3. Whew, okay. Caught ourselves making that mistake. So sorry. This is in 3. So now we go back to here. We know that M0 is 0. So again, we actually could have said that right away from the fact that the inequality from the semi-smallness condition. But now we know for absolute certain. And in fact, we know that M2 is equal to 0. And so this push forward is just straight up equal to, and we know that M1 is equal to 1. So we know that this push forward is just straight up equal to, our IC of 1. And so finally, to finish determining, so we now understand what we know, by the way, that there's one other trick I didn't mention. For any IC, this will always be supported on the closure. This is a general trick. This will always be supported on the closure. So in other words, if you take stocks of this outside of the closure, it will be 0. So in particular, for IC C1 trivial, its restriction to C2 is automatically trivial. So we're really starting to build a picture of what this of what the sheaf looks like, right? IC1. We know that if we restricted it to C0, it's 0. If we restricted it to C1, we know that we just get a copy of the trivial local system in degree 3. The only thing to check to see what happens is what happens when we restrict this to C0. Oh, by the way, we also knew this part already. We also could have figured out this by easier means, because it's a general fact that if you take this and you restrict it back down to its orbit, you just get that local system shifted in the dimension of the orbit. So that's also another general trick that we could have done much easier. But still, we're learning how to use some tools here. Anyways, the final conclusion is we know that these sheaves are isomorphic to each other. So all we need to do is just figure out, so IC1, take a stock at the 0 matrix. That's just a stock of this at the 0 matrix. But I mentioned before that this will just be the cohomology of the matrix coefficient. Glad you're here. Yeah. Well, I mean, yeah, that's a good thing about the fact that they're recorded. And in fact, you'll maybe it's nice that you see the conclusion at the end, and the fact yeah. So this will just be the cohomology of the fiber. We also computed before that the fiber at 0 is just projective space, but projective space has its cohomology will be one thing in degree 0 and one thing in degree 1. But again, I forgot to put my shift by 3 out in front, so this is all shifted by 3, and this is all shifted by 3, which means this is C3 direct sum C4. And so now, in fact, here's kind of where things finally get interesting, and this highlights an example of what I mean by perverse sheaves detect singularities. Is that the other perverse sheaves were like totally trivial to compute, right? IC0 was just the skyscraper sheaf at 0 in degree 0. IC2 was just the constant sheaf on the whole space in degree 4, right? Because they're basically just end up being shifted local systems because the closures of those orbits were smooth. But now, finally, we see that actually our whatever the IC of 1 is it picks up it again, like had C1 been smooth, it just would have been, maybe I should write these as sheaves instead of copies of C, but had it been smooth, we would have just seen in degree 3, it basically would have just been the constant sheaf on C1, but now it's not, right? We see we're picking up this extra term in degree 4, and that's basically because of the presence of this singularity at the origin. Okay. So, sorry for rushing all through of that matrix coefficient. I hope you enjoy later, and keep in mind I make a few mistakes on the way, but I think I corrected most of them. And also I should let you know, if you're tuned in right now still, I cheated a little bit, and I used the fact that I care about equivariant perverse sheaves a little bit along the way, but I will try to amend these things later. If we look at global sections of a perverse sheaf, roughly speaking, it would only take into consideration the highest dimensional cells, and higher cohomologies would see singularities. I'm not sure. I'm not sure what the answer to that is. Yeah, I'm not actually sure what the answer to that is. Yeah, sorry. I'll think about it. Anyways, that's it for today. Time to go prove theorems, play chess, get jacked. Hopefully the same is true for all of you.